Hi, this is Mrs. Lozano. Do you ever wonder why some solutions are colored pink, blue, green, while some solutions are clear? Well, today we are going to find out. Look at these different colors of nickel solutions, starting from the green in his shaker. There's dark blue, blue, purple, red, another shade of blue, yellow, and finally green, the original solution. So all of these containers have the nickel ion in them. But I wonder what's different. Here it looks like nickel is bonded to 4 water molecules and a sulfate ion. And as we scroll across, they are bonded to different substances. These are called ligands. I have another example for you. Inside this container is copper sulfate. Copper plus 2 ions floating around and sulfate ion floating around. Let's go ahead and see what happens when they add some ammonia. As they add ammonia, you can see it becomes cloudy. That is an indication of a white solid or a precipitate. As he adds more ammonia, it changes again. As you can see, the light blue precipitate dissolves and a dark solution appears. The next slide will show us the chemical reaction in this example. We started with the copper ions dissolved in solution. The sulfate ion is a spectator ion, but not reacting in this case. When copper plus 2 is dissolved in water, it forms interactions with water. Here, water is called the ligand. As we add the ammonia acts as a base and removes a hydrogen ion from water, producing ammonium ion and changing this ligand into hydroxide. Producing this copper 2 hydroxide, which is a white solid. I'm sorry, a light blue solid as it appears. Okay. All right. As we add excess ammonia, the ammonia then displaces these ligands. Since we have excess, it will displace all of them. Producing this tetraamine copper 2 complex, changing the color into a dark blue solution. You can notice here that the change in the ligands changes the colors. Compounds of the transition metals constitute an important group of colored substances used in paint, glass, or precious gems. So you might wonder, what is so special about transition metals? Well, how are they different from other metals? You're right, they have the d orbital. Let's go ahead and learn some definitions. A central metal atom bonded to a group of molecules or ions is a metal complex. If the complex bears a charge, it is an ion or a complex ion. Compounds containing complexes are called coordination compounds. Here's an example of a coordination compound. This is the heme molecule, where you have an iron with some ligands around it. This also forms a complex with oxygen, as it is used in our body. The molecules or ions coordinating with the metals are called ligands. As you can see, all these ligands have lone pairs of electrons that can interact with a central atom. Anions or polar molecules. You must wonder what type of interaction is between the metal and the ligand. Let's review from last year what a Lewis acid is. A Lewis acid accepts electrons, while a Lewis base donates electrons. The bond formed between the Lewis acid and the Lewis base. The ligand would be the Lewis base because it has lone pair of electrons, while the metal is the Lewis acid because it has empty orbitals to accept electrons. As you can see, the metal-ligand bond is greatly altered depending on what type of ligand is bonded to the metal. You can see difference in properties such as color or chemical properties such as ease of oxidation. As you can see, many complexes are richly colored. The color arises from the fact that the complex absorbs some wavelength of visible light. As you can see, this complex ion appears to be purple. This is purple in color because it absorbs light at the center of the visible spectrum. If it absorbs light here, it means it reflects green, blue, and red together is purple. The coordination number. Some metals such as chromium +3, cobalt +3 consistently have the same coordination number, 6, in the case of these two metals. 6 means there are 6 ligands bonded to it. 1, 2, 3, 4, 5, 6. The most commonly encountered numbers are 4 and 6. In this level, you don't have to know how many ligands will bond to the central metal. Now, I'm about to show you why copper can be both light blue with water as a ligand and dark blue with ammonia as a ligand. Do you remember these orbitals? Yes, they are the 5 orbitals of the d sublevel. Remember, you can fit 2 electrons per orbital. Now, as the ligand interacts with the 5 d orbitals, as shown in this orbital diagram, 1, 2, 3, 4, and 5, the ligands split these d orbitals into 2 levels. The interactions between electrons on the ligand and the orbitals on the metal cause differences in energies between the d orbitals in the complex. Here, 3 of the d orbitals go down in a lower energy, while the other 2 goes up. Depending on the ligand attached to chromium, the d orbitals are split in different ways. Here, when chromium is attached to the fluoride ion, it is green, and so on. Now you can understand why some chromiums are green, violet, yellow. Now you can understand why, even though it's the same metal, they can have different colors. The difference in gap between the distance between the orbitals, the d orbitals, produces a wavelength in the visible range. This is why transition metals, which have d orbitals, exhibit color. For this to happen, there must be an empty orbital above for the electron to move. If all the electrons are filled in the orbitals, for example, then the solution will be clear with no color. This is why magnesium plus 2, which have no d orbitals, would be clear. Here, some ligands, such as fluoride, tend to make the gap between the orbitals smaller. Some, like cyanogroups, tend to make it larger. Again, the larger the gap, the shorter the wavelength of light absorbed by electrons jumping from lower energy orbital to a higher one, and as it falls back, it emits the energy. As the gap gets smaller, the light absorbed is of longer wavelength and the shorter wavelength is reflected. Thus, the wavelength of light observed in the complex is longer, closer to the red end of the spectrum. To know the charge of a complex ion, all you have to do is know the charge of the copper, which is a +2, the charge of the ligand, which is 0. +2 plus 0 is equal to +2. This is the charge of the of the complex ion. How do you form a complex ion? It's quite simple, actually. The rule of thumb is all you have to do is double the charge, and that will tell you the amount of ligands. For example, if Ag is +1, you double it, you're going to get 2 ammonias. The charge comes from adding the charge of the ion plus the ligand, and you will get the final charge of the complex ion. Here's an example. Since copper is +2, how many ammonias should we add? Right, double 2 becomes 4. The charge of this whole ligand becomes +2 for the copper, 0 for the ammonia, +2 total. Since silver has a +1, we will double +1 and know that we're going to get 2 cyanide ions for this complex. +1 minus 1 times 2 equals a -1 overall charge for the ion. Iron has a +3 charge, double the 3, gives you 6 water ligands, and the whole complex ion +3 plus 0 equals +3 charge. The most common ligands are numbers 4 and 6. And remember, for the AP exam, they will not care what number you add here. All they want you to know is that a complex ion is reached when you add the ligand in excess. And you can have any number on here. You might wonder, how do we name complex ions? Let me give you an example. Tetra means you have 4 ligands, amine is the name for ammonia, and zinc is the metal, and the +2 is its charge. So this is called tetraamine zinc 2. Sometimes they use Latin roots. For example, here we have 2 cyanos, ligands, argentate, argent for the silver, and the 8 saying it's a -1. Again, you don't have to know how to name complex ions. You just have to be familiar with them. So if you see them, you're not confused. I hope this PowerPoint helped you understand how to form complex ions and why different solutions give different colors. Thank you.